Today we are going to see this topic that you see on the screen. I am going to call it frequency response method and the body plots. So let's begin with the simple system that you have in the that I have drawn over here, and I am going to write in here system. Okay, this is system. This could have a transfer function, obviously, just as for the sake of example, your system, I'm going to do it outside so that we don't the system, let's call it transfer function, would be something like 1 over, just for the sake of example, s plus 1 times s plus 5, let's say something like that, yeah? Okay, for the sake of example, yeah. What we have in here, this is my input, right? I'm gonna call it I of s in here. This is my transfer function. I'm going to do it like that, and this one is going to be our output. Okay, so we're gonna call it output of s. Okay, what I propose right now is that we do an experiment in here, and we say, let's say for the sake of example, we come in here and we are going to give the system an input in here. Let's say that my input is some sinusoidal function that just is simple like this, yeah? Okay, the question is, when is on the other side of the output, is the response going to be exactly like the input? Okay, for example, in an accelerometer, you want that the output would be the same as the input because you are actually measuring the input, right? That's the case. But if we put a sine function on the input, would the output be a sine function also? Chances is that it will. However, that output function is going to be influenced by the system dynamics. So it is possible that the output over here may not be exactly, but might be shifted a little bit. You know, this one could be like this, eh? So do you see the difference? They are not the same. There is, if I plot the original on this one, see, this is a very basic concept. The original one was like this, see? So you see, this has a what we call a phase angle, meaning it's either ahead of it or is delayed. So it's leading or is lagging. These are words that we need to use at this point. So what I propose that we do is we say, okay, if we could make an experiment where we could make an experiment where we say, okay, I am going to give it, instead of just one cycle, I will give one that has, more cycles like this. And I would measure the output that also is going to have more cycles, but this output is going to be out of phase, see? So do you realize here we are measuring two things? Is the amplitude of the input, let's just put the letter A for the sake of example. is it the same as the amplitude over here? Yeah, this is the amplitude of the output. So we have two things to measure. So I'm gonna write it down here, two variables to look at. One is the magnitude, and the other would be the phase angle. You know what I just said? If phase is how displaced or how ahead or how delayed is your signal output in relationship to the input. We already know that the transfer function, as you see here, is going to be the relationship of the output of S to the input of S. Yeah, always is like that. That's the definition of a transfer function. But you see, I can come back here and say, oh, I am going to start here at, the frequency here, like we did 1 hertz. Maybe this one is 10 hertz, like this. Yeah, this is 10 hertz, and this one I'm gonna give it now a big one, lots of them, like this. And I'm going to say F is equal to 100 cycles per second. And I keep going. So sooner or later, we need to relate these two quantities together. Okay, the question is, can we come up with a plot? Because say, can we summarize in a plot that would have in here you will have the magnitude. Okay, this is gonna be frequency in here, where you will have let's say 1 hertz, which is 10 to the 0, 10 to the 1, 10, 100, 1000, and 10,000. And in here would be the amplitude. Alright, and on the same under the same consideration, we do another plot. We do this plot where it says this is also 10 to the, is 1, 10 to the 1, 10 square, 10 third, and 10 fourth, like this. And this is going to be your phase angle. Okay, whatever these plots come out to be, in whichever shape they come out to be, these plots that you see here are called body plots. Body obviously is the name of a person, of a scientist that discovered this method. Now, what do I pretend to do with this? How could this be useful? Well, it turns out that if you have a system and this system has its own natural frequencies, right? And you do a sweep of inputs from 1 hertz to infinity, well, sooner or later you will hit those frequencies of the system. And what we want is to be able to find those, and we will be able to analyze whether the amplitude of the system is actually the same, the output amplitude is the same as the input, and in what range of frequencies it is. Because, like for example, in an accelerometer, you want the accelerometer to measure the input will have to be exactly the same as the output, because if it isn't, it's not measuring right. So you need to discover within which range of frequencies the input is the same as the output. Well, obviously this has to do with controls too, because you are controlling what the output should be, or you would say at this point exploring what the output should be. So what is important at this moment is that you understand the concept of the frequency response and the body plot. It's called frequency response because we do a sweep of inputs and frequencies on the left hand side, and we are asking ourselves what is the output. Here are the input frequencies, here slowly, faster, faster and faster and faster, and infinitely large. And this is the set of the response, you see. So I think it's very important that we understand this concept of input system, and then we have the output, and in here we have the idea is to make a plot of the on how this would look. And the way we will see it in here is that plots might look like this. We go perhaps go like that, or this one may go like this, or something like that, where we have the angle between 0 and 90 degrees, or between 0 and 180 degrees, depending what those values are. The concept here is that this magnitude plot and this phase plot, this is what makes up the body plots. Okay, so I would like to give you a little presentation now that follows this basic explanation on what the body plots are, what the frequency response is. So let's go take a look at that. And on the screen we have this analyzer in here. This is an instrument that can measure these responses from a system. So what we are going to do is, let's say, put a device on a table, and then put a bunch of accelerometers measuring devices on how that system moves, and each one of those is plugged into this device. So maybe what I should do is just do a little sketch of this, of what I think, of the way I think this will happen. And let me just go over here, and perhaps we do it in a little bigger scale in here. What I'm trying to say is that if you have a let me just put, I'm gonna do it with the red pen. Let's say and I can tell you from my own experience, because I actually saw how people do this in industry. You have a table in here that looks like this, okay, and this table, in this table you can put a device like a printer or some. So this would be your vibrating table, moves like this in both directions, looks more or less like this. Yeah, so this is your frequency in there, and connected on your device with accelerometers, you connect to here on different parts of the system like this. See, this was one of my first jobs that I had when I worked for IBM, and looking at the frequency response in this table in here, you vary the motion of this back and forth like this from 1 hertz to infinity, if we call, or less than 1 hertz. From 0 to infinity really is to infinity, and you want to record that. That's you want to record in such a way that you will be able to do your plot where you say frequency and you will say magnitude here, and you need to do the other plot where you say frequency and then you have your phase. And then, given this information, you are to make more sense of how the system behaves and what kind of control system you could apply. But the very basic concept of the body plot is, as I told you, is actually quite simple. We need to get it. We're going to get it right. Okay, here is a little bit more of expanded explanation, you may say. And here you have the system drawing in there that you can actually see. Okay, I'm sorry here. Yeah. Okay. This is your system, yeah? It has a damping and a spring, and it has a mass in here. Do you see the input in here? See, this is the displacement, yeah? And then you have in here a force. So here this notation is to say this is the magnitude with this angle, and here comes the magnitude output with the output angle. Maybe you can see it on the left hand side, I mean down here better. This is your input in here, yeah? And it has, let's say, if you measure it from the vertical axis to the peak, that you determine that's phi sub I. Okay, and then if you look at the signal here, do you see these two are not the same? They look alike. Here you can notice easier. You have this this distance from here, but well, this one is much bigger. So you have either the signal is ahead of the input or is behind. So that's why we call it lead or lag. Okay, and just like we have seen in the past with the other method on like the root locus, it's a matter of tweaking in the coefficients of the characteristic equation of the system to make the system do what we want. And that's the heart of the control systems. Yeah? So let's take a look a little bit more in detail on what I'm trying to tell you. You could have like an input in here for the transfer function, and this is your output right here. Yeah, and then this is how a body plot looks like. See, is a little bit more detailed. This is something that we could test in MATLAB if we like. In fact, it might not be a bad idea that we do this right now. You have this transfer function here on the left hand side. You see it right there, this one. I was written another way, I would say g of s is equal to 1 over s plus 2. This is the kind of thing. So can we do that? Can we reproduce this? So I would do like we have done it in the past. We come back here and basically run our computer to get us the in here, right there. So you go to MATLAB, and we are going to, there is MATLAB 2015 it says. So we'll wait a little bit until it comes up. My objective, entering that transfer function and seeing the body plot. That's the objective right now. So we'll wait until MATLAB comes up, and then we will enter that transfer function into the system. What were the values? We had yeah, right there, 1 over s plus 2, right? That's what it is. So let's just, MATLAB is still waking up, so we'll wait for a couple of moments and hopefully we can use it. I would say just now it's loading across the network and it takes a little while, but once it's in here, the response is actually pretty good. Okay, so here we go. Let's just put that transfer function in here. You have a couple of options on how to do it. One is defining the s as a variable, and then you just enter the transfer function as is. Otherwise, you define the numerator and the denominator. I'm going to do it both ways just to practice, okay? So the numerator is going to be 1, like that. And the denominator is going to be equal to s plus 2, right? So this is a 1 equaling here. And then we're going to put the 1, and then a 2, and then we're going to close this. Fine. So now we're going to say transfer function g is equal to the transfer function of the numerator and the denominator. At this point, the variable g becomes a transfer function variable with a value as displayed on the screen. You see right there? Okay. Just for practicing here, another way of entering the same thing is by defining, first we're going to clear this. So oops. Yeah, we're going to clear. So did you mean clear? Yes, I did. So in here, we could say, you could define that s is equal to the transfer function variable of whenever you see s, make it as is, it is a transfer function variable like this. So when you do this, then you can say that g is equal to 1 divided by s plus 2, right? Just like you want it in there. Instead of entering as a polynomial, you just do it like you want it, and then lo and behold, you have the transfer function the same way. So I suggest you use these two methods of entering the transfer functions in MATLAB. They work really well. But in here, you know, we have the variable g, which is the transfer function. If I say do the body plot of g in like this, then the computer is supposed to do both of those plots, the amplitude as well as the angle, and that's exactly what you have on the screen right now, and that's the body diagram. So you see in here, if you look up to this frequency in here, which is less than 10 hertz, the system basically, you have the magnitude does not change, otherwise it begins going down. And the plotting here of the angle is between 0 and 90 degrees, minus 90 degrees. So depending on the frequency, also you either that signal is ahead of the input or is behind. But this is the very basic concept of the body plot, which is which, you know, it is the purpose of this explanation. So I would encourage you to try different transfer functions. Perhaps we'll do different things. Just for the sake of example, we could just enter a different transfer function. We're going to call it g sub 1, for example. And because s is already defined, here you could say that g sub 1 is, perhaps we could do one that has zeros and have poles, like for example you have s plus 5 like this, and then you have, let's just put it one that is a bit more complex, so you can see the power of this, an s plus 10, something like that. And then you could say this whole thing is let's see, parentheses are good, right? So if this is the numerator of the transfer function, it is a good idea to keep it in parentheses, because now you could say divided by, you could divide it by, and then we're going to do another parenthesis for the, say, s plus 5, and then times s plus 9, and then times the order is s plus 4, let's see. So if you, and then we need to close parentheses, of course, so that we don't mess up. And this is the transfer function that we are dealing with right now. So you see, it would be hard for us to go and just with experiment at one frequency record the phase and the angle, another frequency do the same thing, and another frequency do the same thing. But that's exactly what we used to do in the past. But now, if I say body of my transfer function g sub 1, please show it to me, because MATLAB is gonna have it will do another plot. So you go here, say do this please, and in just a few seconds immediately I get the answer. So that's the concept of the body diagram, and we will see in another video how we go about using it for designing controls.